Hey guys, what's up? Eddie Aho here with KissAnalog.com. Guys, today I want to talk about capacitor banks. These big old guys, right? Like, how much capacitance do you really need? Now, Lucas, AVP, a viewer on the channel here, he asked a question. He's from the Netherlands. Thanks for asking the question. I think I'm going to start doing a series where if you're a Patreon or a YouTube member, and if you want to see a video of me answering a question, give me a question. And if I find something like Lucas here asked for, I'll do a video on it. Because, this is a very pertinent issue. Like, I hear guys all the time on my comment section talking about capacitor sizing. And, maybe not all the time, but, Now, I did a design series where I showed how to choose a diode, how to choose a capacitor, how to choose a transformer, and how the transformer gets loaded down and the regulation of the transformer. Some people don't understand the transformers have a regulation thing. And we're talking about low frequency switchers, right? Some people call them linear power supplies. Big old Troy transformers, big old capacitors and that. These are low frequency switchers unless you put a linear regulator on it. Then they become linear power supplies. I just want to keep pushing that point because these are low frequency switchers. I did a video, okay? And it is how much capacitance is needed or whatever. I'll put the link down below because I'm going to show you some pictures from that video. And I'm going to talk about these sizes, but I hope what you're going to like about this is I'm going to give you a formula that I'm going to give you a value, okay, a real simple formula that you can use to size your capacitor banks depending on how many amps you need for your output for your amplifier, okay? Do you need 4 amps, 5 amps, 8 amps, 10 amps? I'm going to give you a very simple formula that for every 1 amp, how much capacitance you need, okay? Depending on how much ripple voltage you want. And we're going to talk about more of that after this video, okay? I'm going to talk about ripple voltage and how much I think you should have, or at least a range or whatever. And we're going to talk about after we jump in this video, okay? So let's jump into this. I don't want to make it too long. I'm going to try to make shorter videos this year. So I'm going to try to be a little more brief, okay? Let me know what you think about that. All right, guys, give me your comments. Really appreciate it. And thanks for watching. Okay, let's get in the video. Oh, and give a likes up. That really helps the videos a lot. If you find any value in a video like this, these design videos, they just don't do very well. I did a series, like I said, I think 7 videos talking about how to design a power supply, the transformer and everything, how to select the parts. Showed you where to find them, things like that. But they just weren't watched very much. And so but I want to do design videos. I've been a power supply designer for years and years. So switching power supplies, not this simple stuff for audio. Audio stuff is kind of on the simple side. It was, but now we're getting to switching power supplies. That's where it's at, guys. But no, if you like the low frequency switchers, I would say let's regulate one. I want to do, you guys want to see a project where I actually do a regulated power supply for an audio amplifier, for a big old, Class A, B, Class A amplifier? Let me know, okay? If I get enough likes, enough, people asking for it, I'll do a video series on that. It's going to cost money to buy the box and stuff. I got transformers. I got lots of transformers. And as a matter of fact, maybe I need to start selling some of those to you guys that want to do some big amplifier projects. But anyways, let's get in this video. I'm already making it too long. Alright guys, this is from that video that I did before. Links down below again. So what we have is we have the mixing scope. We're going to look at waveforms. I'm using this power supply board that I've built up since then. And what I have is I have bridge rectifier over here on the left. Okay, 4 diodes, There's actually 8, 4 on each side. There's 4 capacitors on this side, 4 on that side. The first one's installed up here in the left corner. On this side, none. I have this guy right here just kind of wired in with this black and red wire just for this video. And then I have this one in the video where I parallel into it, okay? And so I talk about that in the video, but I'm using this differential probe over here on the right, this MIG-SIG differential probe. I'm looking at the input waveforms coming off of the toroidal transformer. So we're going to look at the voltage waveforms, we're going to look at current waveforms, okay? And then I've got, there's another differential probe off the screen, but there's some other probes over here on the output voltages, okay? And that one, we're really what we want to pay attention to is the current and the input waveform, okay? So, and I have this variac, this B&K, that I'm going to use to power it. And by the way, I'm going to sell this if anybody's interested. And so yeah, so that's our setup for now. You can see another differential probe right here. I don't think I've got that one set up though. So there's probably one off camera over here on the right. But okay, so now let me show you some waveforms. Okay guys, so here's the waveforms. What I want you to pay attention to, there's a lot of stuff going on. Just ignore the big one in the middle. I should have left that off the screen. Didn't really offer any information on this video or the one that I did before. But the screen waveform, the sinusoid, is the output of that transformer, okay? So that's the voltage. And the voltage here is 10 volts per division. So the center, all these waveforms are centered right here where my cursor is, okay? So this is 10, 20, 30, almost 40 volts peak. So 40 volts peak to peak. So 1, 2, 3, 4. So 40 volts peak to peak. And you notice the sine wave's not very rounded on top. And that's because the other waveform that's important is this purple one, okay? The current waveform. So down here, it's at 1 amp, okay? So this is 1 amp per division, which is right here. And we're 1 amp below the waveform, okay? That's where it's putting out current to the load. And then it gets charged. And you see this pulse come up here and then drop. And that width of that pulse down here is the width of this kind of flat spot on top. What happens is it's pulling this big pulse of current through here, which is 1 amp per division. So it's 1, 2, 3, 4, 5 amps up here almost. Where it's pulling this pulse of current, there's some DC resistance in the transformer coil, right? And the output in the secondary winding. And that DC resistance has voltage drop, which is what we're seeing here. So instead of coming up like it should, there's a voltage drop and it kind of flattens off. But you notice how it kind of slopes up a little bit? That's because as the current peaks right here, it's in the middle, and then as it starts to drop, the waveform starts to go up, okay? So that's kind of what's happening there. One cycle, we could say, okay, this AC waveform crosses 0 right here. Comes up, down, and then comes to cross 0 going in the upward direction like it did over here. So that's a cycle from here to here, okay? But you notice there's 2 purple waveforms in that cycle because the positive pulse goes up and then the negative. See the negative waveforms down here, but the bridge rectifier is going to flip that over so it's going to be on top, right? So the current, I show that. I should have shown a voltage probe on the other side of the bridge rectifiers to show the green one, and then maybe I should have used this blue one that goes straight to show that it's another pulse here. So it would have been on top of this green one, and then it would have came down here and gone up again, came down again. Now, something maybe to know is this one is 1 amp, goes down below 1 amp, a little bit more than 1 amp, then up a little bit. This next one's not quite 1 amp, and the next one's kind of more like this first one. So if we had more cycles, we might kind of see some pattern, okay? But also this yellow one,
this yellow one is the voltage of the ripple waveform on top of the voltage. Okay, so it's AC coupled, so we're just seeing the ripple part. And so what we see is when this purple pulse goes up here on the left, we see the yellow ramps up. From right here, the pulse goes up, we see a nice linear ramp because the current's going up. It's almost linear, right? It's almost a straight line. So the yellow one climbs up, charges up, and then right here where it starts to drop, it drops too. And now this flat part here is the same time frame. See, the time starts right here on this side and then ends down here, which ends right here at the flat spot. So during this flat spot, we can say we had 1 amp. So we can use this in our math formula for the slope of the current in this formula I'm going to show you. So the change of voltage is from here to here, okay? Change of current is from here to here, which is just 1 amp, okay? So we have 1 amp, and what's the voltage? So this yellow one is up here. It's 200 millivolts per division. So it's 200, 400, 600, 800. It's a little bit more than a volt, but over here it's a little bit less than a volt. So it kind of changes. So let's say 1 volt, okay, and we got 1 amp, okay, and maybe we have a little bit more than 1 amp just because it slopes down a bit. I don't know. It's hard to say. So there we could use that. We could also use a rising edge. We could say from here up to here it's the same. Well, it's actually a little bit different voltage because see, each one of these waves are a little bit different. So if we set from here to here, that's about 1 volt, right? And then we could say, okay, the current changed from down here about 1 amp to up here where it's 1, 2, 3, 4. So it almost changed 5 amps from down here to here during this same thing. So we could say, oh man, current changed 5 amps. So that's a little harder to say because this might have a little curve to it. It's kind of a little bit harder to read. So it might be better to use this. The formula is going to come out the same. Okay. The time frame between here and here is shorter. This time frame is longer. Okay. This is only 1 amp. So 1 amp times this time frame is going to be equal to whatever current this is times this time. It's going to be a current seconds balance. Okay, so the current here and here, it's going to be close to that. Well, now it makes me want to go back and look at that picture. All right, so see where the current clamp is? The current clamp is on this wire going to the capacitor. So the current coming from this board is coming through the board down here, and then it's going to go out here to the output. So there's 1 amp going this way. So we're not really seeing that 1 amp. All we're seeing is the current going into and out of the capacitor. Yeah, this pulse of current is only going to the capacitor, and the pulse of current is going out of the capacitors. Okay guys, this is the Mauser website. This is a chemic capacitor now owned by Yageo. Yageo? Anyway, that's what it looks like. Zoomed in. You guys have seen them. There's snap-in type terminals here. $13.50 US. Quantities 1. You buy them in 10s, it goes down $1. Okay, so let's go look at some specs. Okay, this is the data sheet for the ALC 80 105C. Okay, that's what it looks like. Looks like some of those ones we see called audio capacitors, right? One of the big things that people don't point out is this is good for 9,000 hours on this live test. It's at 105C, and a lot of capacitors are only 1,000, 2,000 hours. So 4,000 is usually considered great. 9,000's excellent. So it also says excellent surge voltage capacity. Okay. Here's the size, codes, and so on. We're looking at the 400 volt range. Okay. This guy over here. Let's just go down here. The diameter of 40 to 50 millimeters for operational lifetime gives you this many hours, 9,000 hours. That's a rated voltage and ripple current. Now, if it's just the voltage at 105, it can go up to 14,000. So keeping the ripple current down is big. This right here talks about the endurance test. See, test duration 2,000 hours. This is some specifications. We can cover that if you like in another video, okay? I think we will. So let me know what you guys think down below. Just kind of scrolling through, you see the snap-on turn modes. Some of them have different configuration, more pins. That's to give more mechanical stability. Okay, let's go down. Over here on the left is voltage DC. So let's go down 400 volts. Okay, 400 volts. And the one the guy had picked out was the 2200 microfarad. So 45 millimeter by 105 millimeters long. Okay, so pretty good sized capacitor, right? I mean, not real big around, not like the big old Coke can size, but still pretty big. Just shy of 2 inches and 4 or 5 inches long, I guess, about 4 inches long. Okay, ripple current, very important, 7 amps. Okay, this is 100. See if you come up here and look at the top of the table. At high frequency, like for switchers 10 kilohertz or above, you might be looking at this. The current goes up to 16 amps. Okay, now ESR right over here is 60 milliohms, and you come up here, that's at 100 hertz. Next to it, it says impedance maximum 10 kilohertz, and you come down and it is 32. So that's why it can do higher current. It has lower impedance at 10 kiloohms. Just want to point that out. Well, if you got 50 amps or something and you got 7 amps here, then you're going to need 7 of them minimum. So, and you want to go always above. You don't want to operate at max. So you're probably going to need 8 of these guys.
All right, guys. So what do you think? If you want 1 volt ripple peak to peak, around 6.5 millifarads of capacitance per amp. Okay. Now, here's the thing: is 1 volt ripple is not very much ripple. You know, if you have a transformer that only gives you a peak voltage close to what voltage you want on your rails, maybe you ought to pick a bigger transformer with more voltage so you can allow the voltage to have more ripple. So you don't need as big a capacitor, right? It's just a lot of surge current and all that kind of stuff. But the thing is it'll save you money on capacitors. Just when you pick out transformer, get a transformer with a little more voltage on it. But that's the formula. 1 volt. I don't recommend going less than 1 volt of ripple. I know that, you know, if you get a 25 volt transformer and you're like, God, but I really want 30, you know, close to 35 volts as stiff as I can get, because my audio waveform is going to come up and I don't want it to hit the rail. When the rail's dipping down, I don't want them to hit each other. So I don't want it to flat top, because then your amplifier flat tops a little sooner, right? So if you can hold the voltage rail up higher so your waveform can come up, your amplifier output can come up without flat topping, hitting the rails, then you get more power, right? So I get it. But, you know, by just putting a whole bunch of capacitance on there, at a certain point, like, if you guys want to see another video where I can show you the pros and cons of ripple voltage, let me know, okay? But I think a couple volts of ripple is fine. And you know what? If you want me to open up an amplifier, like I have some pretty good amplifiers. I have an Adcom, I think it's a 535. If you want to look inside that, you want me to do a video where I take some measurements to see how much ripple they allow in their amplifier, or what the power supply looks like in there, yeah, let me know if you guys want to see videos like that. I'll open them up, we'll take some measurements. But I got to see some comments down there, some people, you know, more than 2 or 3 people saying, yeah, I want to see that. All right, so give me your comments, give the thumbs up to the video if you liked it. And guys, what's really cool about this It doesn't matter if you have 25 volts or 50 volts a rail. If you want 1 volt peak to peak, that formula around 6 millifarads, 6.5 millifarads per amp. So if you're going to have 8 amps, like our friend Lucas, if he's going to have, I think he said, shoot, I didn't write it down, but I think he said he wanted around 8 amps. So if you have a 4 ohm load, if you're trying to get some power out, then 8 times 6, okay? So now the other thing is, when I showed you that specification for that capacitor, each capacitor can allow so much ripple current, right? So if you're going to do that 1 volt, 1 amp, let's say it's, what was it, say 10 amps of ripple, then you want each capacitor to be able to handle at least 10 amps of ripple. So anyway, that's an important part of this process, is making sure the capacitors can handle that. ESR. Do you guys want a little short video on ESR, why it's important? And it might be not exactly what you're thinking. For audio stuff, for low frequency switchers, it's different than a switching power supply. A little bit different idea behind it. So, but people get these, you know, these tech terms, ESR, and they're like, hey, let's get low ESR. THD, let's do that. And so I think we all know that THD 0.0000, you know, that's ridiculous, right? I remember back in the day, man, the more zeros the better. I was like, why? Anyway, ESR, kind of a similar kind of thing. So I can do a short video on that too. All right, guys. So yeah, if you want a video on ESR, I think I do want to do at least one more video where I talk about the ripple voltage and how much voltage. So let me know in the comments if you agree, okay? Hey, thanks for watching the video. 2 big thumbs up to my patrons. Really appreciate you guys. 2 big thumbs up to my YouTube members. You guys help support this channel, and the people that hit that super thank you button. There's a little super thank you button down there, guys. Really appreciate that. Had somebody hit it this year already. Thanks so much. I'm gonna put his name right here. All right, guys. Thanks for watching. Really appreciate it. And we'll catch you next time.